Optimization algorithms rely a lot on solving system of equations that are defined by the optimality conditions. If the system of equations is linear, we can rely on Gaussian elimination to solve it. If the system of equations is nonlinear, then we need to use Newton's method. In this video, we illustrate the idea of Newton's methods when the problem has only one variable, so to solve one equation with one variable. Let's consider this simple example where we have to find the zero of the function x squared minus 2, which is plotted on this slide. Newton's method is an iterative method. It starts with a candidate. Here we have x equals 2 as a candidate. And of course, it's not a solution because f of 2 is not equal to 0. So what the method does is to calculate the tangent of the function at x2. So it's a line. And now we solve the problem for the linear specification. So we basically try to find where does this line intersects the x-axis. And this is here. Now we need to check if this is a solution of our problem. No, it's not. Well, because we used only an approximation of the function. So what we do is we start again. We take this point as a new iterate, and we apply the same idea. We calculate a tangent of the function at the new iterate, and we check where this tangent intersects the x-axis. And visually, you see that after 2 iterations, we are pretty close, actually, to the solution, to the point where the function intersects the x-axis. If you look at the iterates, so we provide here a table with the 5 first iterates, where the first column reports the iteration number, the second column provides the value of x, the third one the value of f of x, and the last one the value of the derivative, which is the slope of the tangent. As you can see from this column, the value of f of x goes down to something which is very close to 0. So the machine precision of a computer is usually 10 to the minus 16. So we have reached the machine precision here. What you can see as well is that the precision that we have double at each iteration, almost. So 3, 6, 12, and then 16. So we are here in the presence of a method that goes quite fast. It goes very fast towards the solution. Formally speaking, we will say that the method is quadratically convergent. Somehow the precision doubles at each iteration. So we have a very fast method. It's like a Ferrari. So let's try to interpret this in terms of approximation of the function using Taylor's theorem. The idea of the tangent is that it is a good approximation of the function in the neighborhood of the point where we calculate it. So we call it a model. It's a simplification of the function that we can use instead of the function. And we use Taylor's theorem to develop this model. So we suppose that we are at a point x hat. The model of the function around x hat is given by the value of the function at x hat plus x minus x hat times the derivative of f at x hat. Actually, these are the first 2 terms of the Taylor expansions. So we truncate the Taylor's expansion after the first order. So let's take an example. If f of x is equal to x squared minus 2, like we had on the slides before, so f prime of x is equal to 2x. So remember, in the first iteration, we had x hat, which was equal to 2. So the linear model at that point, which is denoted by m x hat of x, is given by f of x hat. So if x hat is equal to 2, f of 2 is equal to 2, plus x minus x hat, x minus 2, times the derivative of f calculated at x hat, which is equal to 4. So this is equal to 2 plus 4x minus 8, which is equal to minus 6 plus 4x. And this is the equation of the tangent of the function at the point x hat. So this is what we use as a model of the function. And what Newton's method does is to find the zero of this model, so the point at which the tangent intersects the x-axis, and consider it as the next iterate. So this is plotted on this chart. Okay, so we have x equals 2, we have the function, and I've plotted the equation that I've just calculated that corresponds well, as we discussed, to the tangent of the function at x equals 2. So the idea of the algorithm is that at each iteration, the next iterate solves the equation that says that the model around xk of x is equal to 0. So let's do this. So it means that we have f of xk plus xk plus 1 minus xk times f prime of xk equals 0. So xk plus 1 minus xk times f prime of xk is equal to minus f of xk. Now let's assume that the derivative is not 0, and we can divide by it then. So we have xk plus 1 minus xk equals minus f of xk divided by f prime of xk. And finally, I move the xk to the right part, and I obtain the definition of the iteration, which says that xk plus 1 is equal to xk minus f of xk divided by f prime of xk. So this is the definition of an iteration of Newton's method. It is well defined if the derivatives at xk is non-zero. So let's apply it on another example, which happens to be arctangent of x. So we do the same. We start from x0 here. We calculate the value of the function at x0. It's not 0, so we need to apply an iteration of the algorithm. We calculate the tangent, and this tangent intersects the x-axis at the next iterate x1. Again, x1 is not a solution yet because the value of the function is not 0, so we start the process again. We calculate the tangent, and we obtain x2. Well, note that in this example, x2 actually is further away from the solution, which is here, than x0 was. So it seems that we are going away from the solution. Well, let's continue. Again, we calculate the tangent here, and we have x3, which is even further away from the solution. And actually, if you continue this process, you will see that the iterates of this algorithm will go further and further away from the solution, and they will tend to infinity by positive and negative values. So this does not work. So our Ferrari actually is crashing in this example. So this is a specificity of Newton's method. It's a fast method when it works, but it does not always work. It may not converge in some cases, like we showed on this example. So convergence will be guaranteed only when some specific conditions will be met. In this video, we have introduced the ideas of Newton's method, which is a method that is designed to find the zeros of a nonlinear equation. It does so iteratively, and at each iteration, it calculates a linear model of the function at the current iterate. And then it calculates the zero of the linear model, which is an easy task. This generates the next iterate. And we have seen that when the method works, when it converges, it may do so very quickly, but it does not always work.